So in the previous lecture, we had looked at these iso rate lines. So this arises from a plot of conversion against temperature. And to obtain these lines, we simply took the reaction kinetics. So if it's a first order reversible reaction, then we could simply write RA is K1 CA, and we can rewrite that as CA naught 1 minus X minus K2CB, which is Ca naught X. So the temperature dependence is behind these K1 and K2s, and of course conversion is there. So we could fix the reaction rate, and we could look at the relationship between X and T through this equation when we fix this reaction rate. So that's how we got these curved lines. And of course, the reaction equilibrium line is one of the special cases of that equation. And we identified that as a line we wanted to avoid, because that's where the Nets rate is zero. And of course, we don't want a reactor that's operating with a zero reaction rate. So we want a nice high reaction rate in the reactor, because that means we accomplish some kind of conversion in a small space. So we had also plotted the reactor energy balance. So here's this line in x of t, which resulted from the energy balance. So that was the energy balance given in the usual form. So that was the adiabatic equation. So that's basically our operating line for the reactor. And as we consider increasing volume along, for example, a CSTR, we progress along this line, achieving higher conversions. And we noted that as we achieved different conversions along this line, the reaction rate was changing. And of course, as we start nearing this equilibrium line, or this equilibrium point, that specific point which is accessible to this reactor, as we get closer there, the reaction rate progressively reduces. So if we look at our general CSTR mass balance, we can normally write an FA in times X equals RAV. And so if we want to achieve a certain X, or let's say we want to achieve as high a conversion as possible, then the fact that as we are progressing in here, that the reaction rate is going down, then we can see for small changes in X, we require a much greater volume, because the reaction rate is so low. So once more, if we regard this as a fixed number, then if we are operating close to equilibrium, that means this number is going to be very small, which means to be equal to this, the volume is very large. Or another way to say it is, as we get closer and closer to a point where the reaction rate is zero, the volume goes off to infinity. So, of course, it's not reasonable to try to approach this equilibrium point. And on top of which, we can see regions here where the reaction rate is not zero, but it appears to be inaccessible to us. And the plot I'm showing here is for this example where we started with a temperature of 250 Kelvin. And if you think about that, that's actually a refrigerated fluid, and it's quite expensive to refrigerate things on a plant. You normally think about a stream that's available around 300 or 320 Kelvin. So that's normally a starting point. But if you take that case, you can see that our operating line is going to have the same slope. If you look at the energy balance, it's a line like this. And in this case, we achieve an even smaller overall conversion. So there appears to be an issue with us trying to achieve higher conversions. And that's something we want to address today. We want to develop some methods that will allow us to achieve high conversions in the face of this obstruction by the equilibrium. And of course, the equilibrium can't be crossed, because as we get closer to this point, of course, the reaction rate goes down, so the driving force is killed, and so basically we can't cross this line if we're starting here. So we have to think about a way to design around this, and maybe let's leave that at the back of our mind while we consider the other side of this. So we've talked now about this exothermic reaction, but let's go a bit further and take this also for the endothermic case. So that was the plot we got for the exothermic reaction. If we were to switch around these rate constants and consider the reactant fluid entering at 450 Kelvin, then the plot looks like this. So you see the line slope the other way, right? So just looking up here, you can see for exothermic reactions, it slopes like this. For endothermic reactions, the equilibrium line slopes like this, and here are some isorate lines plotted. And you can see also the driving force or the design equation line, the energy balance on the reactor that also slopes this way. So we can see that the system, of course, is always trying to go off to equilibrium. So the tendency is that when we start building things and letting things react in the space, it is going to try to reach equilibrium. So what we want to do is ride that force. So there's a driving force towards equilibrium. We want to ride that force, but we also want to access these higher regions here. So let's think about how we can do that, and maybe just pause the video and see if you can come up with some strategies for doing that. Okay, so hopefully you've thought about that a little bit, and you've realized that, well, we could simply look at cooling down our reaction mixture. So if that's our reactor, we could think simply of adding a heat exchanger in here. And so let's say we added a cooler after this reactor, then you see we would basically be achieving a reduction in temperature, and after that we could introduce another reactor in the series. So if we simply cool the mixture exiting that first reactor, and if we assume that the reaction isn't really happening here, and in practical terms, this could mean that that we require a catalyst in the first reactor for a reaction to happen to some significant degree, or it could be that the time, the residence time that's required to go from here to here is short enough that there isn't much time for reaction. Whatever the reason is, there isn't much reaction happening here, and yet there's some cooling happening. So if we are just cooling, so let's say the first reactor had a volume that corresponded to this conversion and temperature. So if we manage to cool that mixture from this point, and let's say we cooled all the way back to 250 Kelvin, so let's say we stopped there. So again, we have to work out then what heat load is required, how much energy must we remove from the system to achieve that temperature change, and we can do that. We've got the temperature change here, and we know about the heat capacity of the reaction mixture here, so we can work out the energy required to do that. So let's say, so basically we can design this heat exchanger such that we achieve a reduction in temperature here, like so. So we've restored the entry temperature here to 250. So we have a 250 here, we had a 250 here, and we have a 3, let's say that's a 320. So we entered the reactor at 250. Because it's an exothermic reaction, the temperature will rise to 320, accomplishing a conversion of let's say 0.26. And then we cool the mixture. So because we are just cooling and we aren't reacting, the conversion will not change. So the conversion stays on 0.26, whereas the temperature drops to 250. So that's our new starting point. And then if we also have another catalytic reactor here, then that can react further. And we'll prove just now that that will increase on a line that's parallel to the first one. So you see, that's how we can achieve higher conversions. that's how we can access these other regions on our isorate line graph. And of course, there's nothing to stop us introducing yet another cooler here. So we have a cooler here, and then we could introduce another reactor over here. And so we can indeed step up along this line. Of course, we should bear in mind the expenses involved. So cooling to this degree, cooling all the way to 250 Kelvin, that's pretty expensive. And each new line here is a new reactor. So we have to consider the costs of constructing all this and weigh that against the benefit of achieving a higher conversion. So if we achieve a nice high conversion, then that means eventually coming out of the train here, we'll have a high concentration of the product B and a low concentration of A. And if B is a valuable product, then that means we don't have as much separation to do. We don't need to separate as much B from A for this to be a reasonable product. So that is one strategy that we could apply here. So interstage cooling, that's how we term this. And that's an effective way of achieving higher conversions. And of course, at each stage, we have to realize that each of these CSTRs there is going to be a particular volume associated with the point that we've chosen here. And we have to use the design equation to work that out. And another thing to point out is that in this reactor system, remember if it's a CSTR, right, by definition, we have perfect mixing in that reactor, which means that if we choose any point in that reactor, we are going to get the same temperature and the same concentration. So all points in that reactor have the same temperature and the same concentration, whereas we entered at some other temperature T in and some other conversion X naught. So that effectively means we've started at this point, and then the moment we are in that reactor, we are at this other point. So this line, points along this line can't be found inside this reactor. You can't find, if this reactor is designed to achieve this conversion, you go instantaneously from your entry point to this point. That means we don't have the advantage of perhaps higher reaction rates along the way and so on. So that's a characteristic of the CSTR. And then, of course, if we consider a plug flow reactor, on the other hand, plug flow reactor will show us points where we go through the intermediate stages. So if we take a point near the entry, then we know that we will see low values around here. And then if we consider points near the middle, we'll get some other values and so on. So we will be able to observe all these intermediate concentrations across the plug flow reactor. We'll observe the intermediate temperatures also. So all these are observable in the plug flow reactor, and they are not observable in the CSTR. And this can be significant because, and we've mentioned this point many times before on the course, that this means there are regions in the PFR where the rate will be higher than other regions. And this can result in a significantly lower overall required volume for a plug flow reactor as compared with the CSTR. So calculation of the volume of these reactors is not quite easy to see on this graph, right? Because this is really, there are really three variables of importance on this graph, right? We've got xt and then also the reaction rate. So the reaction rate, we also have to imagine our way around by kind of mentally interpolating between these iso rate lines. So the plug flow reactor and the CSTR, the volumes for the CSTR, we just look up that end of the line to get the volume of that. Whereas for the plug flow reactor, we can see we need to integrate along this line to find its overall volume. Anyway, we'll come back to the calculation of the reactor volumes a little later in the same lecture. For now, we've established one way of accessing higher conversion, so that's through interstage cooling. Can you think of another way to access higher regions? And to do that, just think about this equation. Remember, this is the equation of the adiabat, right? So this is the equation of this operating line on our curve. So if we just look at this equation, you could say that we've addressed this part of the equation in interstage cooling, right? It's not really part of this equation, right? Sort of next to the reactor, we've installed a heat exchanger, so we've changed the inlet temperatures and so on. Could we apply any other changes in this operating line for us to access higher regions? So I'll let you pause the video there, and you can have a think about that. And when you're ready, we'll carry on and talk about another strategy. So hopefully you've come up with the alternative, which is that if we consider this equation, we can see that, well, temperature we've already talked about, and there isn't much we can do with this heat of reaction. So our reaction temperature, our heat of reaction, that's dependent on the species that are reacting, and we take those as a given. So we aren't talking about totally changing what we are trying to react. So there's not much we can do here. Whereas here, we can see that we have some choice, right? We can choose the inlet molar flow ratio here. And furthermore, we can see that this factor is going to change the slope of our line. So this will give us, we can get a steeper slope. So remember, dx dt is basically this factor. So if we could get a larger value here, then we could achieve a sharper slope of x in t. And all we have to do then is figure out how to increase this value. Now, of course, we wouldn't really consider just feeding more of the product into the reactor because, number one, the product may or may not have a higher heat capacity, which would allow us to increase the slope. And also, we don't want to dilute the reaction mixture with product, especially with this being a reversible reaction. We could, however, consider simply introducing another component into the system, something that doesn't react. So if we introduce an inert component with a high heat capacity, then the sum here will be a larger number. So in other words, the equation would look like this, right? So our driving force line, which is the sum in theta I CPI of the heat of reaction in T minus T in. If we introduce a high heat capacity inert, then we would have basically theta A, which we know is 1, then CPA, plus theta I CPI divided by the heat of reaction and multiplied with the rest of it. Then basically we could choose the slope of this line. So we could simply pick a slope that looks more attractive to us. So let's say we said, okay, we're starting here, we know that, but let's say we wanted to reach this conversion and temperature in just one reactor. So let's say we selected this to be our slope now. So we could simply look up the slope. We can say, okay, this is the slope for 0.5 and a difference of 50 degrees here. So we can say dx dt, so the desired slope dx dt T is equal to, and the change in X there is 0.45, and the temperature, and it's the temperature change here, so it's 300 minus 250, so that's 50 Kelvin. So that's our slope, and if we look at this equation here, dx dt is simply going to be this stuff here, so that's equal to theta a cpa plus theta I cpi over the heat of reaction. And so, of course, this is a constant. We can't change this, and we are feeding component A in, and that beta A is going to be a 1, and it has a certain heat capacity, so we can't change this either. But we are free to pick this. So if we have specified a desirable slope, then we can simply solve this equation for theta I. And of course, theta I is not bounded. It's not the case that this is a fraction that has to be between 0 and 1. Remember, theta I is simply the molar flow rate introduced at the inlet. Sorry, that should be I. The molar flow rate of I at the inlet divided by the molar flow rate of A at the inlet. So we solve this equation for theta I, and then we just multiply by FA in, and that tells us what molar flow rate of inert to use to achieve the slope that we like. And you see here we are already saving one reactor by doing this. So there are significant savings to be done there, to be had there. But of course, if we are increasing the molar flow rate of component I, there are certain costs associated with that. And so we have to consider those costs and see when it starts to become unfeasible and so on. So hopefully to accomplish such a change, this is a feasible flow rate for component I. And remember, I is not being used up in the system. It's an inert, so it can simply be recycled. So it's not unreasonable to say we could use high flow rates of component I through the system. We could also raise the concern, well, doesn't that dilute A as well? And yes, the concentration may go down if we are fixed in what the total flow rate should be. But still, we should be able to accomplish a higher conversion. So two strategies we have now to navigate our way through this plane and accomplish high conversions. We can see if we are stuck to this inlet, this minimum temperature, that there's only so far we can go still. But still, that's much better than where we were, which was being constrained to this point here. So we have some idea now on how we can navigate this plane. But let's extend that to developing our reactor designs. So basically, we want to select our volumes that will help us accomplish this change. So far, we've talked about it fairly intuitively. So we can't predict how we can use these operating lines, but let's see how we can translate that into a real design. So let's take, to begin with, the continuous stirred tank reactor. So we've derived and we've shown that that is the design equation. So let's just put that in here, and let's consider how we can calculate this volume. So if we just expand this out, noting that our reaction rate is the difference between the forward rate minus the reverse. That's a K1C2 minus K2CB, which is equal to K1CA. We can say CA in 1 minus X minus K2 CA in times X. So we can say that if we have chosen, let's say we've started with that same example, so we entered at 250 and we have chosen a point here. Let's say this is what we've chosen as our exiting conversion, say 25%. Then the required volume to accomplish that is equal to, so that's FA in times x, so 25% for x, and this RA we will write as K1. And noting that K1 is a temperature function, so there's that, and then CA in 1 minus x, and then minus K2 CA in x. And of course, K2 is also a temperature function. So when we choose this conversion 25%, then we also look up the temperature for that line. So perhaps that's 310. So we would use a value of 310 in here. And remember that those functions are simply the Arrhenius versions. So for that example, we were given the Arrhenius relationship. So we just stick the temperature in here, and that returns for us K1 and K2. So that's defined, and then the only other variable there is what we've already defined, namely x, so 0.25. So you see, all that is sufficient for us to calculate the volume. And so as we mentioned, there is just the one point, right? According to this equation, we just choose the operating conversion and temperature for that reactor, and we can get the volume for that. Now, when we introduced the interstage cooling, we said, well, we could cool back here, and then we drew a line that was parallel to this without really justifying it. So we want to establish what is the gradient of this line. So to answer that question, what we can do is draw out a CSTR system. Let's start by doing that. So let's look at the CSTR system with interstage cooling. So there's a feed and there's a product line. And let's say we then wanted to, I'm just picking another color here. So if we drew our energy, our control volume, let's say we drew our control volume like this. Excuse me. So we drew this control volume, and the energy balance for that control volume then applies, of course. So that's the line that we currently have here. And then what we could do when trying to work out what this line would look like, what we could do is simply draw a box from the inlet point right across like so. And now, of course, we also do have this this heat exchanger, and there is heat being added to this box. So we should extend this. So we can say this line is actually like so. So there is heat crossing the boundaries because the heat exchanger, that temperature difference is external to this box. And then we can see one big reactor and some cooling going on. Now, if we go to our design equation, not the design equation, the energy balance, right, just looking back here for the energy balance, let's just pull this out. So if we pull the energy balance in here, we can see that the gradient of the line dx dt, sorry, the gradient which is dx dt is only dependent on the inlet molar flow ratio and the heat of reaction. So of course the heat of reaction we are taking as a constant. We are saying that the delta Cp is small enough that we can ignore that part. So we are taking heat of reaction as a constant, which means that the only thing that could change the slope of the line is this theta I Cpi. And you would normally say, yes, but my inlet flow ratio at this point is different. So my inlet molar flow ratio here is not the same as the inlet molar flow ratio here, because this was pure A, whereas because of reaction, we now have A and B in this line. So it looks like there will be a different slope if we were to consider this reactor individually. So if we were to plot a separate operating line just for this reactor, it is true that the gradient will be different. However, we haven't done that. What we've done is drawn an overall box like this, and we are now saying that this value x, this conversion, is the overall conversion. In other words, if I were to label this stream as 0 and this stream as 1 and this is 2 and this is 3, we are saying that we could define x3 in terms of so x3 is the conversion by the time we reach the exit point. So we could define that x3 in terms of the inlet to that reactor. So we could say this is FA2 minus FA3 over FA2, or we could define it instead. So let's just call that, let's just distinguish for conversion like that. Or we could define the overall conversion, x3, in terms of the flow rate here and flow rate here. So if we were to write this instead as FA naught minus FA3 over FA naught, then you see that's the overall conversion. So for the whole reactor train, that's the conversion we achieve, whereas this is the individual reactor. So if we are defining conversion in terms of the overall translation from the entry to the exit, then the correct value for theta I will be those values used at the entry point here. In other words, there will be no difference between the theta I that we use for this reactor and the theta I that we would use for that whole system. Right, so that's number one, the first reason why the slope won't change. So that acknowledges that this x is the overall conversion. So that's a special definition for x now, the overall conversion for our reactor system. We also have to account for this energy that was added. Now, when we were talking about the stepping up procedure using interstage cooling, so we were stepping up to that point and then we cooled down the system by changing the temperature in this way, then we stepped up. Then we considered the interstage cooler as being between those two reactors. But now if we are looking at an overall system where, in effect, this heat exchanger is hidden from us and all we can see is heat being removed from the system, then we could say simply, well, we could regard this heat as being removed from the entry of the reactor in the first place. So we could say, well, what if we were to remove the heat from the system before it even entered the train? So if we look at what happens between the two reactors, the temperature drops from this value to this value. So if we take that same temperature drop and apply it just at the entry point, so let's say it was here, well, it's probably somewhere back here, right? So if we did the cooling before we even entered the first reactor, we'd be somewhere here. And then we applied this overall conversion. So we know we are achieving some overall conversion x3, and that happens with the overall temperature T0 to T3, then in effect, that's this line. So this overall reactor with the cooler is represented by the single line, and that is actually the same as the reaction happening in the one reactor here and then being cooled, so that happens there. And then because we are regarding the x in here as being the overall x, then that's in effect taking us up here. And all of that is equivalent to cooling down the whole system here and then taking the overall conversion like that. So we need to understand this because number one, we have to justify ourselves when we take the second line as being parallel to the first one. And in addition to that, we also do need we need to calculate the volume of the second reactor as well. So we also need this volume. And so now that we've justified what this means, we are allowed to say, well, I can then just take the same design equation. We need to write V2 is equal to FA in. So that's the molar flow rate in at this point. It's not the molar flow rate at that point. So the molar flow rate to the whole train of reactors, and then we have to get the change in number of moles due to the second volume. So if we want the second volume only, then we need to know the molar change across that reactor. So we would take the overall conversion there minus the overall conversion there. So we can write that as XA3. And then the conversion at this point is the same as the conversion at this point. So that's minus XA1. And the reaction rate then must be the rate that we accomplish under the conditions in that reactor. So the temperature in that reactor is this temperature, is this temperature. So when we look up the temperature, it's the rate. It's the rate that we achieve at this point. So this is RA3. So that gives us a way to calculate the volume of that second tank in the series. Right, so that's what we can do for the CSTR. Now, things are a little different when we consider the plug flow reactor. So let's replicate all this in the case of the plug flow reactor. So we've discussed how we could navigate our way up through this plane, and we've talked about the two possibilities, and now we know how to compute the reactor volumes for those two cases. However, there is also a third thing that we could do. And of course, we've applied the adiabatic assumption in developing these lines. So if we go back to the energy balance, of course, we could, instead of using adiabatic relationships, we could say, well, we could add a jacket to our CSTR. And if we do that, we'll have this additional term for Q dot, so the heat transferred due to the presence of the jacket. That will also change our design equation. And of course, if we choose U and A to be large enough, then we get an improvement on the slope. And of course, it's not quite as straightforward as this case. You can see this is, well, it's still a straight line, but we have this additional term that's going to change our slope, and in this case, the intercept as well because of this. So this is a third thing that we can do. So we can add heat, and that will help us shift our way. So well, we have added heat here, but I'm saying if we also add heat to the reaction zone itself, then that's another way of moving ourselves around on this plane. So anyway, we will analyze for that more carefully later. So right now, let's look at calculating the volume for the plug flow reactor case. So we see in this case that we require the integral of 1 over the reaction rate in order to calculate this volume. So you see here, the volume is FA in times the integral of XA in 1 over RA. And if you consider this line, you can see that RA is, so let's say this was the plug flow reactor line. And as we mentioned, that for the plug flow reactor case, we can in fact find all those points in the reactor. So in contrast with the CSTR case, where the whole reactor was operating at that one at that one point, I think it was more there. In the plug flow reactor, we will have parts of the reactor where the temperature will have a value down here, and the temperature will be different here and here. And likewise, the conversions, we won't have the same concentration over the whole reactor. So in other words, we will have all those points along this line in that plug flow reactor. And that means we will have a variety of conversions here. and also the reaction rate is varying along this line. And we can see here that the volume requires us to get the volume, we have to integrate this function like so. So we can think about some ways of doing this numerically. So let's just magnify it down here. So let's say we had this line to integrate along. So let's say we picked some points along this line. So this is still the xt plane, and we are integrating along this line. Then, of course, we can look up at each point what the conversion is. So if we have an x1 here, and then there's also a certain reaction rate there, R1, and then we have an x2 and an R2 there, and so on. Then we can approximate the integral along the line. So this is the line where the endpoint is the same here, and we've just discretized our way along this line. So we are saying that the volume will be approximately what we can get by taking FA in and multiplying it with a numerical approximation to this. So we could take this as the sum of delta xi over ri. And of course, to evaluate this, we can take, so delta x could be, let's take this panel as an example. So between these 2 points, you can say delta x is equal to x3 minus x2. And then ri, well, if we look on the graph, we can try and estimate an r value. So, but you can see it's quite imprecise. We have to approximate some value in between these. So it's going to be better to use our equation. So we can say RA is K1 CA naught 1 minus X minus K2 CA naught X. And we need K1 and K2. So remember, that's a function of temperature. And we can look up these temperatures here. And in this case, you see we are trying to evaluate the rate down here. So in this region, we need to approximate this 1 over Ri. And we don't want to use one of these points. We want some average rate over this space here. And perhaps an approximation that we could use there is take the average temperature over this range and the average conversion over that range. So we can take, if we take simply the linear average over that, so that's just T2 plus T3 over 2, and average conversion like that, x2 plus x3 over 2. Then the average rate over that interval would be K1. So the average rate will be K1 evaluated at T average there times CA naught 1 minus X average also, and then minus K2 at the average temperature times CA naught times X average. So we can approximate the rate over that interval, and we do know the difference in conversion there. So we just stick those into this equation, and so that's the contribution from this part of that line. And so we do that for each part, and we just add all those up, and that value will be the volume of the plug flow reactor required. Right, so that's the PFR, and of course the usual applies that we could have interstage cooling, so we can do interstage cooling for the plug flow reactor as well. and we can have more plug flow reactors like that. So all those proofs and so on about the using the overall conversion that still applies here. So the same approach of cooling down and then taking a line that's parallel to the other, that all applies in this plug flow reactor case also. Right, so that's the PFR, and then of course we want to think about the batch reactor as well. So here's the batch reactor, and if we look at this equation, we can see here that we've got that same integral. So we do have the same integral, and this time we also have this variable t. So we do have to choose the time that we want one cycle to take. So if we want to convert, if we want to accomplish a conversion XA within time t, so let's say we specify 2 hours, then we fix those values and then we perform this integration much like we did for the PFR, and that will tell us how big the batch reactor needs to be in that case. So just by analogy, I'll mention how we can get the volume of the batch reactor, but there is more that's possible with the batch reactor. So later in the course, we'll talk about controlling the batch reactor, applying heating and cooling to really optimize our way around that curve. Well, optimization is really the subject of the next section. So to expand on that, we now know how to find the volumes of a CSTR and a PFR and a batch reactor in the face of needing to navigate our way through this plane. So we can see that we can possibly access the other regions, and we can work out the volumes that we need to do that. But of course, we would like to optimize those volumes. So we can see that possibly, although we may just pick values here, we don't know whether those are the best choices for those values. And you see there are many, many degrees of freedom here. I mean, we could choose not to cool all the way down to 250. We could cool to somewhere there. Maybe that's a better choice. And then we could react. It's basically a matter of choice where to stop along this line. So the next question is there not some more established ways? Is there not some way of or some algorithm that will help us make good choices? So at the moment, it's wide open. It's a completely open-ended problem, but we would like some guiding principles that will help us reduce the overall volume of our reactor system. So that's the subject of the next lecture.